Sometimes data comes in the form of a contingency table. Here's an example. What's special about a contingency table is that there are simultaneous classification of more than one characteristic. In this example, two characteristics or variables are involved, and each variable is split into two or more categories. The row represents the various categories for the first variable, and the columns represent the various categories of the second variable. And the frequencies are reported according to the various rows and column combinations. Hence, this is also known as cross-classification or cross-tabulated data. When data is presented in the form of a contingency table, the natural question to ask is there a relationship between the two variables, or is there not? To answer that, chi-square analysis can be used to test the independence of the two variables. The null hypothesis may be stated as the two variables are independent of each other, meaning there is no relationship. And the alternative hypothesis will take on the opposite spectrum, which is they are not independent of each other. There are some key terms that you need to know when doing tests for independence. We know that the sample data comes as a contingency table. The first variable A is split into R rows, from A sub 1, A sub 2 to A sub R. And the second variable B is split into C columns, from B sub 1, B sub 2 to B sub C. These data are captured as the observed frequencies, where O sub ij is the frequency of the cross-classification of the ith row and the jth column. All the O's in each row should add up to n sub I naught, and all the O's in each column should add up to n sub naught j. Next, we find the marginal probability p sub j's. These p sub j's are the proportion that are in each column. To get p sub j, we take the column total n sub naught j and divide it by the overall total of n. For example, to get p sub 2, we take the total for the second column and divide by n. All these p sub i's should add up to 1. And the theoretical number that we expect to get for each category are called the expected frequencies E sub ij's. Assuming that the null hypothesis is true and the two variables are really independent, then using the joint and marginal probability concept, these E sub ij's can be calculated using the formula P sub j times the respective row total n sub I naught. For example, to get E sub 2c, we take P sub c times the second row total. Now, if the variables are really independent, then the observed frequencies should be comparable to the theoretically predicted ones. Therefore, the idea behind the test for independence is really about comparing the observed frequencies with the expected frequencies. So how do we go about comparing the observed and the expected frequencies? We can use our trusted procedure for hypothesis testing. Step 1. Based on the given scenario, we come up with the null and alternative hypothesis. To test if the two variables are independent, we use the chi-square distribution for our analysis. Step 2. Specify the level of significance alpha, which corresponds to this right tail area that is the rejection region. Next, state the degree of freedom df, which is equal to r minus 1 times c minus 1, where r is equal to the number of rows in the contingency table and c is equal to the number of columns in the contingency table. Using alpha and the degree of freedom, we can find the critical chi-square value with the use of the chi-square table. And that critical chi-square value separates the rejection and the non-rejection region. Next, step 3. We find the test statistics chi-square star using this formula, which is the summation of the squared difference between the observed and the expected frequency, divided by the expected frequency for each row and each column. Finally, step 4. Draw the conclusion. If the test statistics is greater than the critical value, then the null hypothesis is rejected at alpha level of significance. Otherwise, it is not rejected.